Okay, let's make a start. So for the Unit 1 and 2 stuff, I just realised, hang on, I think I might have got a bit of double audio going on. Yes, okay, that's better. Okay, yes, Unit 1 and 2 stuff is the circular functions and exponentials logarithms test, so we're going to be continuing on with that. I believe this is the last week, unless anyone has a different schedule. I'm going off of one student's planner so far to understand how far the Unit 1 and 2 schedule has been going, and I believe this is the last week prior to doing this SAC. So let's continue practicing. So we've been doing a couple of questions already for this sort of stuff. We did question 1 already, we did question 2 already. Let's have a look at the question 3. So we've got a Ferris wheel going on. There is a function h of t which gives the height in terms of meters, height of a person at a time, okay, height above the ground of a person, and t is in terms of seconds. So we see the ground given by the horizontal black line, and we can see different varying measurements of what that might look like. Whereas if it was here, that would be a 2 meter above the ground. And then this measurement here is less obvious what that's pointing at, because this one's directly, we can see, lined up, or at least lined up closely enough with a person's head. This one not so much, so I guess we'll see with more detail perhaps. Anyway, we have the function. It is a cosine. How long does it take the Ferris wheel to make one complete revolution? This is a circular function. There is one key quality of circular functions that dictates how long it will take to complete a single cycle. What quality is that? Yeah, anyhow? I think you're having a bit of a tech issue thing. Yeah, you came off mute, no audio. And I think your camera's also trying to do something.
Okay, I think it works now.
Yep,
so
that's better.
the millimeters, I think, is pointing to the top of the dotted circle.
Top of the dotted circle. Oh yeah.
The dash.
Sure.
Looks to be the height of the head.
Oh yes. Okay, I see. Yeah, good point. Good point. Yeah, it's pretty accurate actually. That's probably what it was referring to, from top to bottom basically, and that would be yeah, that's actually supported by the function itself. If we dive into the vertical translation plus amplitude, we could see that that would be the case. Indeed, actually, yes. Nice. But for part A, how long does it take for the Ferris wheel to make one complete revolution? There's a certain way of calculating this for any circular function, how long it takes to complete a single cycle.
It's the period, so
yep.
2 pi over n, and n is going to be pi over 30.
That's it, yeah, whatever that coefficient is that's attached to the x, or I guess in this case attached to the t. So 2 pi.
So it's a minute. 60 seconds.
60 seconds, yeah, correct. We're giving seconds, of course, because that is the unit of time provided to us. Brilliant. That's a fairly fast cycling Ferris wheel. But anyway, part B, sketch the graph. Yeah, this will be tech active, so no bother so much. If we talk just sort of verbally, out like how you might do this in a tech-free way, or at least maybe some expectations about what the graph would look like before we sketch it, we can see we've got a vertical translation of 11 and an amplitude of 9, which means the midline of our circular function will be at y equals 11, and then plus or minus 9 on top and bottom. That's why the y equals 20 lining up with this head makes a lot of sense now, because 11 plus 9 gets you to 20, the absolute maximum it could possibly be. And 11 minus 9 gets you to the 2, which is the absolute minimum that it could be. So you'd expect this circular function to oscillate between 2 and 20 as its minimum and maximum. And we would expect maybe a domain of 0 to 60 or of something to that effect. So let's go ahead and do exactly that. 11 plus 9 cosine pi on 30 bracket x, wait, actually maybe multiply x, take 10. And yeah, there's also a shift right by 10. Knowing roughly what you expect the range of values to be makes it easier for you to set the scale on your axis. Like for instance, if we know a full cycle is done in 0 to 60, maybe just for visual clarity it would do 0 to 120, just to get an idea of the whole thing that we're looking at. You could even then take it a step further if all you wanted to do was see exactly the effective one cycle, and you could do it like that. Starting t equals 0 typically makes sense. And now we should see it pretty much starts and stops at more or less the exact same location. Even though it's at a different point along the cycle, they still end at the same net horizontal location. And that's what it says, sketch for one revolution, so you're able to identify or choose what revolution, what domain you would like to use. Part C, state the range. We kind of already talked about this one already. It's going to be 2 to 20. At what times is the person at a height of 2 meters above the ground? A couple of ways you can now do this with the graph that we have. One way to get a quick and dirty answer would be to use the graph analysis tools. We already know the minimum is going to be 2 meters, and so the minimum of this graph is therefore 2 meters, and finding the time value at which we have that minimum by using the graph tools will give us x equals 40, or in this case t equals 40, which would correspond to 40 seconds. Alternatively, if you don't use the graphing tools, because let's say it gives you a value that's decimal, this is now just a cas solve, right? It's saying there's a height of 2 meters, which is a y value. So you set y equals 2, and see what comes out. We'll get the same result, of course. This exact same procedure can be propagated onto part E when you've got 15.5 meters above the ground, which is likely going to have more solutions, and it's a little bit more unwieldy to try and do it on the graphing tool. But we still do get exactly x equals 0, 20, and 60 as our results there. If we wanted to, we could kind of visually validate that we've done something okay, setting our height value 15.5. There's just a little drawn line, and you can see, okay, it definitely touches there, there, and there. We're expecting 3 solutions, and sure enough, we got 3 solutions. That's pretty much it. Let's skip ahead to an exponential one. Okay. Question 6. Forest fire. I saw a flicker. Was there like a hand raised? If so, let me know. A forest fire has burned out 30 hectares by 11 AM. It then spreads according to the following exponential equation. H of t is the area burned. Time is in hours after 11 AM. Find h when t equals 0, t equals 1, t equals 2. Again, these are very standard questions. You define the function in your CAS, and if it says find h, that means find the y value, and if it says find h when t equals 0, it means shove in t equals 0. So let's first go ahead and define the function. 30 times bracket 1.65 power of x, and then precisely h of 0, h of 1, h of 2. And those become your answers. A little bit more interesting question in part B. Find k such that h of t plus 1 is equal to kh of t. This one I'll let you guys think about a bit more. It's not super crazy, but definitely a step up from just sub in a value.
Do we just use a solve function and shove the value in and solve for k?
Yes, that's exactly what we would do. We would write down precisely what is written on the equation in a CAS solve for k. That's exactly right. Nicely done. H of bracket x plus 1 is equal to k times h of x, comma k. That gets us our k value. Nice. Part C, how long does it take for 900 hectares to be burned? This is basically the opposite of part A, which is instead of having a time value to sub in, you have a hectares value, a y value to sub in, and the opposite is what we're solving for. You're solving for time. So this will be a CAS solve. The equation is equal to 900. 900 equals function, comma x, and in this case we do get a nasty logarithm answer there, so I don't think it's intended to give an exact. Maybe they intended a number of decimal places, and so if we do that, we're looking at 6.7, maybe like 6.8 hours. And it doesn't necessarily say at what time does that occur, more so just how long. So you would just give a number of hours rather than converting that to a time value. It's a bit of a shame they didn't actually make use of the whole hours after 11 AM. But oh well. And lastly, sketching the graph of h against t. Before we even bother doing that, we can have a look at the base and seeing that it's between 0, it's after 0 and 1. It will be a rising exponential. It'll rise from left to right, and there's no reflection terms, so it will definitely rise from left to right. The coefficient only seeks to influence where that x equals 0 the y-intercept is going to be. And so when we set our scale again, we're going to make sure we at least include y equals 30 in there, but likely a lot more. Okay. H of x. If we do it, we'll see it quite rapidly increases. If we set exactly y equals 30, we're only going to hit our x-intercept barely. Oh, sorry, the y-intercept barely. And so we'll basically just continue on like that. And yeah, there's no vertical translation to this, there's no plus or minus term at the end of the function, so we're going to have our asymptote at y equals 0. Cool. Question 4. Yeah, we could do question 4. Okay, this time we have a cosine giving the voltage in a circuit. Sketch the graph, I think we'll ignore. Part B, find the first time the voltage is 60. This will just be a matter of showing in V equals 60, CAS solving. More interested in part C, which is finding all the times at which the voltage is maximized. How might we do that one?
Sketching to find maximums.
Yep, Fmax. Fmax will be a good idea here. Finding all the times. Now the interesting thing here is that there isn't really a given domain for this sort of thing. So finding all the times likely means getting a general solution going. So let's see if Fmax can achieve that. Define the function first. 120 cos 60 pi times x Fmax function comma x. Yeah, it actually does. N over 30. So if I did h of 0, I should get a max, which I do. If I do h of 1 over 30, I should get a max, which I do. Negative 1 over 30 should get a max, and that pattern will continue for any integer n. So that would be the general solution that you give. Sweet. Okay. N 1 over 30 means, so that's the general solution to the circular function, because basically if you have no limit on the domain, you would have infinite solutions, and so you need to have some variable that basically stands in for the number of revolutions that you're the number of revolution that you're on, right? So like the first revolution would be n equals 0, which is why I've done 0 over 30, you know, h of 0, getting your first maximum. Then choosing positive 1 and negative 1 would be the next revolution forward or the next revolution backwards. So I was just sort of validating that the n, the solution that was given was actually valid. Do we need to recap on general solutions, or is that okay? Okay. Question 5. Figure shows a water wheel rotating at 4 revolutions per minute. Distance d in meters from a point is... oh, okay, cool. So the distance is given by this equation, which is fully unknown. And so distance in meters from a point P from the surface of the water. Yeah, okay, that makes sense. So basically as this wheel rotates in a anti-clockwise direction, the distance from that point to the water will shrink, go negative, actually. Negative, getting closer and closer to 0, and then positive. So it'll continue in that sort of cycle. The circular function that we're given is fully unknown, so our goal is going to be to basically follow our nose in part A to solve each of these terms. First up, the period. So there is a piece of information there that is directly related to the period. What is the period of the circular function?
Two pi.
2 pi. Why 2
Wait, sorry.
pi?
What was the question? What was the question again?
So that what's the period of this circular function that we're going to have?
Oh, sorry. I was just saying the standard period.
Yeah, no, that's fair. I gotcha. 2 pi is the standard period, absolutely. There's a piece of information in here that'll help us grab a specific value for this period.
The radius is 3 meters.
The radius is 3, yeah?
Yeah, so I guess we can find the actually no, that doesn't really help much, does it?
It helps with something else, yeah. Just not the period necessarily.
So the the equation's only in variables, so is it 2 pi over c?
2 pi over c. Yes, the period will be 2 pi over c. Yes. That would be how this equation gets written in terms of just the question terms. Yeah.
Would it be 15?
Could you repeat that, sorry?
Since it says 4 revolutions per minute, every single revolution is 15 seconds.
Yes. That's better. So 4 revolutions per minute. Yes, every revolution will be 15 seconds, and a revolution is a period. So this will be equivalent to 15. T is in terms of seconds, so yes, we're going to use seconds here. And so yeah, the answer to AI, to be clear, is going to be 15. Still doing your 2 pi over c is going to be helpful for solving triple I, which we can now see we've created an equation that just has c in it on its own. And so solving for c, it's going to be a matter of doing a bit of a flip, rearranging. So you're going to have 2 pi on 15 is equal to c, and finally, actually that's it, 2 pi on 15. There's no simplifying that one further. And so that'll get us both I and triple I there. Double I, the amplitude. There was a piece of information that was mentioned earlier that can help us grab the amplitude.
Is that 3?
It's going to be 3, yeah. So the radius of the circle itself. That's because the amplitude is the plus minus difference that you are changing from your center. And so yeah, it's going to be 3. Amplitude, they've called it B, so we've got B equals 3. Nice. Now, weirdly, they haven't really asked to solve for A, even though it's pretty necessary before moving on to part B. A being our vertical translation. There's one last piece of information we haven't used here. And we'll need that. Yeah, we'll need that before we can do part B. So how are we going to get our vertical translation?
Would it be D A plus 2?
A plus 2.
Or vertical translation as an A
Yeah.
being 2?
Would it be 2? Yeah, that's my question, is going to be 2 exactly, because 2 is the distance between the center of the circle and the bottom. Is it exactly that though?
The question says that the D is the distance D in meters of a point P from the surface of the water.
Yeah.
So it should be 2.
Yeah, but my challenge is that this goes negative. Like it'll have, if you think about what the actual peak will be here, it'll be a peak of 5. It might end up being 2. You're right, I just got to sort of picture it in my head a bit better. The peak of this would be 5 at its absolute maximum. So 5 at its max, and it'll be -1 at its minimum, because 2 from the floor, and then 3, the net difference there being -1. And so the center line will be the vertical translation, which means we have to find the midpoint of these, which means adding them together and dividing by, yeah, okay, that's going to do it. So 5 plus -1 gets you 4, divide by 2 gets you 2. Yeah, it's going to be 2. Cool. So good you guys are able to visualize that a bit better. I just needed to walk that through myself a bit better. But yes, A is 2. Awesome.
Okay, so aren't we supposed to find H?
We are now supposed to find H. That's part B. Yes.
Oh, wait, which one were we doing right now?
So we had just finished the A there, as in like, well, you guys had done it, but I had to work it out in my head a bit better. So yes, we have our A equals 2, we have our B equals 3, we have our C equals 2 pi on 15. Now all that's left is H.
Okay, so wouldn't H be 0 because it's a sine function?
Won't H be 0 because it's sine? Sine starts at a mid-level. It doesn't start at... as in, are you saying like because there's the point 0, 0?
Oh yeah, sorry, I totally forgot to consider the vertical thing.
Okay, yeah, cool.
Yeah.
So the way that'll work for doing this is because we've solved A, B, and C, and we're given D equals 0, T equals 0, that means that all we're going to do is plug in the terms that we know, replace the D and the T with 0, and then whatever comes out will give us our, well, one possible solution for H. So let's go ahead and do exactly that. Many 3, 1, 0 is equal to, so the A was 2 plus the B of 3 sine 2 pi on 15 times 0 for our T minus H. Not H. Can't use that one again. Let's go F, comma F. That's going to give us a bunch of different solutions. maybe we can... What's a good limit here? We had a period of 15, so maybe we can do 0 to 15. 0 less than x less than or equal to 15. No, that's not good either.
Not just 0x3.
0x3. Maybe I actually should have done... Say again?
Is that not the highest? It can be 3.
The highest it could be is 3 as a horizontal translation.
From, well, no, 5 the highest. And it can be
5 is the highest of y value.
yeah. So then, oh no, nothing.
Yeah. Maybe I should have actually put f on this instead. Okay, that's a bit closer. Yeah, nice. Okay, so it's still going to be nasty little shit like that to get an exact, which it is asking for, exact. So I guess you just give the simplest one here, which would be the first solution over here. Yeah, I wonder what they intended. I'm going to have a quick sneak at the answers, see if they intended anything different. Because it does seem a bit weird, some of the exact answers that we get. Yeah, they gave us a decimal. Nice. Ah well, anyway. Sketching the graph, we've already put together all the key terms that are going to be involved. So at this point it's we could have a look at it again, but we can maybe just talk about it instead. Horizontal translation of roughly 1.7. We're not going to really see that, depending on how you set your domain anyway. For a well, actually no, this one will be a domain of 0 to 30, so we'd expect 2 cycles to come out of it. We already talked about the max and mins that we might expect as 5 and -1 respectively. And that's about it for expectations, so let's see how that plays out. Okay, it was 2 plus 3 sine 2 pi on 15 x minus... Okay, I'm going to put in a quick placeholder. That's better. Set it 0 to 30. 0 less than equal to x less than equal to 30, not 33. So we get a bit of what might be a bit of a weird behavior, where a sine starts at its minimum of all things, or at least what looks like its minimum, until we expand out the domain, because we should expect it to hit -1. So yeah, horizontal translation is playing a bit of a role in how the start of the circular function ends up looking. And as we expected, because the period was 15 and we're doing from 0 to 30, we're getting 2 cycles worth out of it.
Sorry, how do you highlight the x value?
So when you go up and down, by default it'll highlight the entire thing. All you do is you toggle either right or left once you're in there, and you can get in more granular, from there, holding shift will grab whatever you're used to it grabbing in a computer sense.
Yeah, I got it. I got it.
Yep.
Thank you.
And then from there it's just Control C, Control V, like a computer.
Yep.
Sweet. Yeah, it's really helpful. Like, I didn't know how to do this when I was doing my studies. I was always having to grab a full copy, delete all this shit, and then maybe like define it so that I could actually use it properly. Yeah, I never knew about Control C, Control V, which I probably should have. But hey. Alright, cool. Question 5 all done. Is 7 gonna be a good idea? A bowl of water is initially at boiling point. Temperature is given by that theta equation. Complete and copy this table. I don't think that's a great idea. It's basically just asking you to say, hey, shove in t equals 0, what do you get? T equals 1, what do you get? So on and so forth. Drawing the graph, again, that would just be a matter of looking at the equation itself. This has a vertical translation of 20 and therefore an asymptote of 20. It's a base of 2, so it would normally be a regular up and to the right exponential. However, it does have a reflection term in there, causing it to reflect across the y-axis. So it will now decay to the right rather than increase to the right. And this coefficient here is just going to, yeah, it's just multiplying the whole thing by 80, basically. So let's see what that ends up looking like. Okay, what do we got? 80 times 2 power of negative x plus 20. It's going to be completely off the scales. So we would want to make sure if our asymptote is 20 and we got a pretty drastic coefficient on the front, maybe we'll hit it up to like 100. And we can see we are indeed decaying to the right, and to the left it'll increase. Now, it's not going to be valid for less than t equals 0, will it? I guess just it's a decent default to assume that anything left of t equals 0 is undefined. Anyway, that's the part B. Part C, at what time is the temperature 60 degrees? This is, again, just pretty trivial stuff. Temperature is our y-axis thing, so that just means a cas solve of setting our temperature value to 60 and figuring out what time that comes with. You don't even... yeah, actually this would have taken maybe a bit of effort to try and steal directly from the function itself, but you can... Actually, yeah, that would be quite a bit more challenging to get directly from the function. I was going to say just by looking at the coefficients you could tell, but it's actually a little bit more challenging than just doing that. Anyway. And then D is the opposite. You're now given a time value and you want to find the heat value. So sub in the time value. Okay. Moving on. Question 8. 3 countries, each of them now has the same population of 70 million. Country A grows uniformly by 30 million in every period of 10 years. Country B, same thing, but 50 million. Country C, multiplied by 1.3. Give an equation of the population for each country at time t. Decent question. We don't usually have a lot of practice creating equations from rule words. So if a population grows uniformly, it means it does so at a constant rate. Right, so if it grows uniformly by 30 million, it means that if you started at 70, then 10 years later you should be at 100, another 10 years later 130, 160, so on. The passage of more time doesn't speed up the rate at which it is growing. And so even just knowing that and working that out in your head gives you an idea of what the rule could be. You don't even have to have an idea what the rule could be. You could just have a bunch of data points. You could say at time t equals 0, you have 70 million. At time t equals 10, you have 100 million. T equals 20, you have 130 million. These are points you could put and dot out and observe what that would look like. Does anyone know what this relationship is? What graph, what function best describes this? Rather, even just the function type. This would be an example of a linear. Whenever something is growing at a constant rate, it means it has a constant gradient, right? And that is the hallmark of linear. So if we have our generic y equals mx plus c, and we have this starting value of, okay, well, when t equals 0, y is 70 million, I now have 70 million for my y. mx disappears because I'm sewing in time t equals 0, so my plus c value is going to be 70 million. Then in my next iteration, when t equals 10, I need 100 million. Well, I now have 100 million is equal to m times 10 plus the 70 million. I can now solve for the gradient. 30 equals 10m, m equals 3. Y equals 3x plus 70. Where each y value is in terms of millions. So again, we should see that if I sub in t equals 0, I get the 70 million, which I do. And if I shove in t equals 10, I should get 100 million, 100 million, which I do. 3 times 10, 30 plus 70. Not necessarily super obvious that it was going to be 3 as the gradient, given that the value that we were told was that it grows by 30 million. Because, you know, if you choose a plus c value of 7, if you know that your plus c value is 70, then maybe you expect your gradient to be 30. The reason it doesn't pan out to be 30 as your gradient is because it's every 10 years, not every 1 year. So because both of them are double digits, so to speak, they kind of cancel each other out. That's one way of thinking about it. Once you've done the exercise already, doing the country B population is now trivial. Right, the only thing that's changed is the 30 is now a 50. The starting line of work is exactly the same, and the final line of work, we can assume we're going to have a gradient of 5, which will work out. So, equation 2, 5x plus 70. Country C is going to be the harder one. It needs to be multiplied by 1.3 every 10 years. So again, getting an idea of what we expect to have happen. We're starting at 70 million. So when I do t equals 0, I should expect 70. When I do t equals 10, I expect 1.3 times the amount. So t equals 10 should get me 91. T equals 20 should get me a further 1.3 times that. If we check the net difference between each of these, this one had a difference, the last 10 years had a difference of 27.3, whereas the first 10 years had a distance of 21. This is evidence of an exponential growth. The gap between things is non-consistent. It's non-uniform, I should say. This is where we would start using an exponential equation to work with. So we start with our generic exponential equation. Y equals a b to the k t. Capital A is our initial value. It's what we start with at t equals 0. So 70 million. B is the growth rate. So if the population is being multiplied by 1.3, the base is now 1.3. K also has to do with growth rate. It's got to do with the duration over which you do your multiplication. And since it's every 10 years, and we're saying t is going to be in terms of years, what we're going to do is set our k value to be 1 over 10. And the reason why is because every integer value of t up until t equals 10, well, sorry, it will take 10 integer values of t, integer rollovers of t, to get to t equals 10. Under which circumstances you now have 10 over 10 as your exponent, simplifying down to 1. Once that simplifies down to 1, you now have 70 times 1.3, which is what we wanted to have happen, right? After 10 years, t equals 10, we have whatever we started with times 1.3. T equals 20, we'll do the next iteration, so on and so forth. These are usually harder to get our heads around, so let me know if that one needed any more explanation. Okay. On the same set of axes, draw the graphs. Sure. So we normally think of exponential as something that grows rapidly, very fast. That's not necessarily always the case, depending on how early it is in its growth. Like we're seeing already, just by looking at the gaps of the last 20 years, they're not particularly large. Like country A and country B had 30 million and 50 million every single 10 years, whereas this one hasn't even reached 30. So exponential growth takes time to compound onto itself. So let's see what all of these graphs end up looking like compared to each other. 3x plus 70. And let's get the scaling good. Okay, what's a good... Let's say we're going to do this over 50 years. We're going to be probably approaching 250 million. Yeah, that sounds about right. Next up was the 5x plus 70, which we'll expect obviously will grow rapidly, faster than the other one. And then lastly we'll have 70 times bracket 1.3 to the power of x over 10. So for a while is lagging behind and eventually surpasses country A, and if we let this go on for longer, we'll eventually surpass country B. So it's not necessarily just a given that exponential will beat linear or any other typograph for that matter. It needs the time to actually achieve it. In fact, that's what question C is asking us. Find the time at which population C is overtaking the populations of A and B. It's very likely that these are going to give decimal values, so it's not necessarily recommended to use the graphing tools in this case. You'd be better served just CAS solving for when the equations equal each other. Excluding the t equals 0, because all of them start out at 70 million here. Okay, so F11 was my exponential. Cool. So we're doing CAS solve F11 equals F9 first for the first country. Okay, we're going to get decimals anyway, so I guess it doesn't really matter. And then F10. So in terms of what you give, since we've done our x in terms of years, we're now looking at 34.8 years and 66.8 years for the different populations. We weren't told a specific year that we started in, so that will be the best you have to give. That's it for question 8. Creating our equations, identifying whether what we had was linear growth or exponential growth, and then exploring the ways in which you can create those equations. Alright, question 9. Bushfire started from a controlled burn, modeled by a basic exponential. The y value is the area burned. T is hours. Find the area burned after 5 hours. Shove in t equals 5. Let me clear up the workspace on this. And we'll start fresh. Function equals 2 to the power of 0.25x. It said find area burned after 5 hours. So let's put in a time value of 5. How many hours, after how many hours will the area burned be equal to 20 kilometers squared? Double checking the units that A is indeed in terms of kilometers squared, which it is. Makes it so that this is once again just a CAS solve, equating the function to 20. Getting our time value, which if you need it exact, you can use that. If you need a decimal, obviously just control enter there. Part C, determine the time interval in which the area burned is between 10 kilometers squared and 30 kilometers squared inclusive. So depending on the function that you're working with here, it can be a bad assumption to just say area burned will always increase. So finding area burned or time at 10 kilometers squared and time at 30 kilometers squared isn't necessarily always the best way to go about it. Like for instance, if it was a polynomial type thing and the fire sort of waxed and waned, it increased and then decreased, increased, decreased. It's not necessarily just a great idea to do time at area equals 10 and time at area equals 30. However, we can see this is an exponential, and exponentials are strictly increasing or strictly decreasing by their nature, and so we are safe enough to just do that. So 10, 30, grab the two values and find the difference. That's our difference, and that's in terms of hours. T hours after the containment, so that's like the duration of time. Time interval, now that I'm looking at it, probably more so means what's your start time and finish time. So it would be something like giving 13 hours to 19 hours. That gives you an actual interval itself. There's no guidance here on rounding or anything, so it's hard for me to say what you should do here. Let's see, how did they round it in the answers? Three decimal places, because why not? But they did want like a upper lower bound rather than just the duration of time. Okay, next up, question 10. Two tanks start to leak. One has a linear leak, the other has an exponential leak. Find V1 0, V2 0. Just by looking at it, they're both going to be 1,000. Shoving in t equals 0 into the exponential causes the exponent to go to 0. Anything to the power of 0 is 1, and therefore 1 times 1,000 is 1,000. Linear is a bit simpler. Putting a 0 there just removes the whole thing. Both of them start out at a volume of 1,000. Sketch the graphs. Sure, we could do that maybe if we need to answer it for part C or something. How much water is in tank A when tank B is empty? Ah, okay. It's a nice enough question. So let's start by making sure we actually have both of our functions defined so we can work with it. And while I'm defining this, if someone would like to take a stab at it, feel free. Okay, how much water is in tank A when tank B is empty? So tank B is given by the second equation, and so forcing it to be empty is a matter of setting the y value, the volume, equal to 0. So let's find out when that actually occurs, and that occurs at x equals 25. From there, all we want to do is understand what the volume is in the first equation, the first tank, at that exact same time. So we take that t value of 25, shove it back in, and just control entering there. We can see we still got 64 litres left. Part D, find times at which the two tanks have equal amounts of water in them. Well, it's going to be at t equals 0. We already know that for volume is 1,000. But the other time, again, could just be solved with the cas, forcing the two functions equal to each other. one of our solutions, we expect, oops, I guess we're not going to get exact here. We're going to get our t equals 0, and in this case t equals 23, which we would observe on the graph if we, well, I guess had time to graph them. Cool. That brings us to time on this one here. We ran through a fair amount of questions. If there's any further clarification, I'll be here for it. Thanks for coming, guys.
Thank you, thank you.
Thanks,
you.
Chris.
Cheers.
Thanks. Have a good day.
You too. Any clarifications? Maybe we're AFK. Okay. If it's something, maybe send it to me via message after chat and after the meeting ends, and I'll have a look at it there. Okay. Bye.